Hello everyone. Welcome to the 10th episode of ZEISS Micro Minutes. I'd like to thank everyone who has joined us for our previous sessions and welcome any newcomers to this one. My name is 𝗶হি𝗵𝗹𝘀 and I am an EM Applications Engineer in the ZEISS Innovation Center, California, the building you can see behind me. I'd like to give everyone a quick introduction to the space that we're in. We're streaming live on YouTube. We welcome questions from everybody. To enter those questions, you should see a chat on the side of your window. You can submit your questions and we'll answer those as soon as we can. So today I'm going to be talking to you about some of the challenges and solutions when it comes to high-resolution imaging on insulating or non-conductive samples. So to really start that conversation, we should talk about sample preparation. So when it comes to mounting a sample, the very common approach is to utilize something like a double-sided carbon tape or a copper tape. And while these tapes have very strong upsides, particularly their mechanical robustness in holding a sample, they're actually very poor conductors when you measure through the thickness of those tapes. And that's very important because when the charged electron beam comes down and interacts with the sample, it's going to have to traverse through the sample and bleed to the ground of the microscope. And if there's this thick layer of non-conductive tape between the sample and the sample holder, well then we're going to have issues with charging. There's a very simple experiment that anyone can perform as shown on this slide. If you just take a multimeter, it doesn't have to be anything special. If you were to measure between a carousel sample holder, which is really what's going to bleed to your stage, and on the other end measure from points where the tape is or perhaps where your sample is, you'll notice that through the thickness of the tape we're actually measuring megaohms of resistance. Meanwhile, if we were to measure through the some sort of colloidal silver paint, we're actually orders of magnitude more conductive, which is really what's recommended when it comes to mounting a sample. So ideally utilizing perhaps a carbon tape or copper tape, and then utilizing colloidal silver or graphite to electrically ground the sample to the sample holder. Of course, you can coat your samples, but we'd like to avoid that, at least for this conversation, because it has the possibility of obscuring information on your sample, depending on how thick that coating is on the sample. So a little bit about what we can do on the operational side to mitigate charging and, in some cases, beam damage onto the sample by achieving what's called charge balance. So this is a rendering that was taken from the Dr. David Joy's book. It's really a wonderful representation of what's happening where we have a charged electron beam coming down and hitting our sample. And as a result, we know that secondary electrons will be generated and leave the sample. Some electrons will be elastically backscattered and leave the sample. So we kind of can start to see that we have negative charge going in and negative charge going out just by imaging the sample. So normally, under most conditions, those are going to be in an imbalance. And any residual charge that remains between what's in versus what's out will be within the sample, and if it's conductive, should conduct down to the ground of the microscope and away from our sample. In the case of insulating samples, we can't rely on that happening. And so if there's any differential of what's coming in versus what's coming out, that's liable to stay on the sample and produce charging artifacts. So if we manipulate this sort of conservation of charge or conservation of currents, we can see that there are relationships between the electrons coming in and the electrons coming out based upon our selection of acceleration voltage. So what's shown here is the total electron yield on the y-axis and the beam energy on the x-axis. And to make a clarification, beam energy on the x-axis we can treat interchangeably with the acceleration voltage for simplicity's sake, because a 1 keV acceleration voltage should produce roughly a 1 keV kinetic energy beam. So when we say 1 keV, we mean a 1 keV acceleration voltage setting. So if we look at the total electron yield, where a total electron yield of 1 means that all the electrons that come in will leave as a result of the signal that's generated, and anything less or more results in charging, either a surplus of negative charge for negative charging or a deficit of negative charge, aka positive charging. We see that there are 2 crossover points where we hit a total electron yield of 1. We refer to those as E1 and E2, and though they both exist mathematically, you can see that E1's energy value on the x-axis is quite low. It's not impossible to achieve on a field emission SEM, but considering that the results are the same as using E2, and E2 is a much more approachable value, we end up using E2. So the workflow of when you load a sample that's insulating, typically you'll start with an acceleration voltage, and you might see that there's charging behavior. You see drifting, or you'll see splotchiness appearing in the image. And so this workflow would have you lower that value. And that starting point was probably around maybe 3 or 4 kV acceleration voltage. As we go lower, we should hope to see some change. If we were in that negative charging regime where that first X was, it might start to become less severe, so the splotchiness might start to recede, drift should start to slow down. And if we keep following that direction, we might see that we went too far for balancing that charge, and there's a reversal of the drift, and the splotchiness might invert, and an overall change in the charging behavior in the sample. And so the overall goal is to find that sort of Goldilocks value of, splitting the difference until you see the reduction of the charging behavior from changing the acceleration voltage. Generally speaking, we can see that the E2 values and E1 values increase linearly for an increase in atomic number. So that kind of can give you an idea if you're looking at something that is higher atomic number versus lower atomic number, though not every material is it important to know this value, because many materials are conductive and we don't care about finding this charge balance. There are a couple of published values that can serve as a good starting point for folks out there. Most of the values for E2 you see on this list range from about 400 volts or 400 EV all the way up to about 3 keV. Now keep in mind that this is a starting value because how the sample is mounted, the sort of electrical grounding that is facilitated during the sample preparation will all have an impact. Not to mention, the sample that you load might have multiple materials on it of different thicknesses and different layups and layers. What's shown on the right side is just an example of one you might see within the semiconductor world of resist on copper, on gallium arsenide. And it really can make things a little bit more complex. So this sort of experimental approach and watching for the behavior to change is really what's advisable. So if energy/acceleration voltage is that broad brushstroke for neutralizing charge and getting a nice high-resolution image on an insulating sample, well then selecting the current is really the fine brushstroke. It does have a bearing on neutralizing charge, but it isn't nearly as impactful as the first parameter that we talked about. Here we're just showing the surface potential, aka the charging, intensity as a function of current for different acceleration voltages. And yes, it makes sense that a higher current for a given energy would induce more charging on an insulating sample. One more thing to mention, if you were to find that E2 value in working conditions that work well for your sample, and you load that in again maybe a week later, the value should not change. Unless, of course, certain topographical effects are having an impact, or perhaps the sample is tilted because there's some stage tilt. Well, that's liable to change the E2 value just because of how much more signal can escape if a sample is tilted versus if it's flat. So this is something to keep in mind. So I'd like to show a couple of images, and after the images I'll show some videos of actually acquiring images on these samples. These samples are an array of typically insulating and beam sensitive samples. All of them are uncoated, and all of them have been approached with the same sort of finding charge balance. So on the left side, we have an uncoated butterfly wing. This is taken at about 400 volts and 6 picoamps, so very low current and generally a low acceleration voltage. And we're zooming all the way into about 85,000x magnification, or about a 1.3 micron horizontal field of view. If we were to look on the right side, you can see some negative photoresist, which is also, in that same sort of class of challenging samples. Similarly at 400 volts and 6 picoamps. And hopefully folks notice that there aren't, splotchy artifacts and the images are crisp, which indicate that there hasn't been charging leading to drifting in the image. Two more images to share with you. These both were taken on a polyethylene battery separator. Here we have an image on the left side that's about 10,000 or 11,000x magnification, and on the right side all the way up to 100,000x magnification. Both images taken at 200 volts and about 6 picoamps of beam current. So now I'd like to show a video or two videos. The first one is going to be the workflow of capturing these sorts of images on the uncoated butterfly wing. And I want to draw special attention to how quickly and easily this can be done with the Gemini column and the ZMCC. So here we have. We will show how a user can quickly and easily collect high-resolution images on a beam-sensitive and non-conductive sample, in this case an uncoated butterfly wing. We'll start this illustration in the exchange position and start our timer. We can utilize the top-down view supplied by the NavCam and the top right view of SmartSEM by double-clicking on the blue sample on the stub, which is that uncoated butterfly wing. We can then change our working distance to be closer to the pole piece and turn on our beam. We start at 5 kV and a few hundred picoamps as an arbitrary starting point, and then quickly jump down to 1 kV and 6 picoamps, which is much more conducive for this beam-sensitive and non-conductive sample. By simply tweaking our focus and stick, we can actually start to see the butterfly wing structure and zoom in. We're going to decrease our working distance to get closer to the pole piece as we drop below 1 kV for the best imaging performance. Here we're dropping down to 400 volts to further reduce charging and to preserve the structure of the butterfly tissue. Now imaging a sub-area, which is the supportive structure between the ridges of the butterfly wing and its substrate. Performing just simple wobble correction, focus, and stick is all that's necessary when changing beam conditions even well below 1 kV. There are no mechanical adjustments or column adjustments that need to be performed when making these changes, as no immersion imaging is used on any of our ZMCC columns, whether that's part of the Sigma family, the ZMCC family, or crossbeam family. This adding to overall speed and ease of use, we can just quickly jump into collecting our images. So here, in less than 4 minutes, we're collecting images at 75,000x magnification, or about a 1.5 micron wide field of view on this non-conductive beam-sensitive butterfly wing at 400 volts and 6 picoamps. We can continue on and collect some images at higher magnification for this sample. Because of the low beam energy that we're utilizing, we can avoid damage to the sample while maintaining very surface-sensitive detail. So it's really as simple as that. You can see that within just a few minutes, we can collect those high-resolution images on this uncoated butterfly wing. What I particularly like about that video is it shows the ability to change beam conditions, both acceleration voltage and current, very easily. And that's really owed to the design of the Gemini column, which exists across the entire ZMCC suite, as well as our Sigma FESEMs and even our crossbeams. The next video I'd like to show, just to show that the workflow is the same and the level of ease is the same, is imaging of that polyethylene battery separator. We will show how a user can quickly and easily collect high-resolution images on a beam-sensitive and non-conductive sample, in this case an uncoated butterfly wing. We'll start this illustration in the exchange position and start our timer. We can utilize the top-down view supplied by the NavCam and the top right view of FIB-SEM by double-clicking on the blue sample on the stub, which is that uncoated butterfly wing. We can then change our working distance to be closer to the pole piece. Sorry about that, folks. I think I played the wrong video. We will show how a user can quickly and easily collect high-resolution images on a beam-sensitive and non-conductive sample, in this case an uncoated butterfly wing. We'll start this illustration in the exchange position and start our timer. We can utilize the top-down view supplied by the NavCam and the top right view of FIB-SEM by double-clicking on the... One second, let me... The user can quickly and easily collect high-resolution images on a beam-sensitive and non-conductive sample, in this case an uncoated butterfly wing. We'll start this illustration in the exchange position and start our timer. We can utilize the top-down view supplied by the NavCam and the top right view of FIB-SEM by double-clicking on the blue sample on the stub, which is that uncoated butterfly wing. We can then change our working distance to be closer to the pole piece and turn on our beam. We start at 5 kV and a few hundred picoamps as an arbitrary starting point, and then quickly jump down to 1 kV and 6 picoamps, which is much more conducive for this beam-sensitive and non-conductive sample. By simply tweaking our focus and stick, we can actually start to see the butterfly wing structure and zoom in. We're going to decrease our working distance to get closer. In this quick video, I'll show how a user can very easily and quickly collect high-resolution images on a beam-sensitive and non-conductive sample, in this case an uncoated polyethylene battery separator. I start this illustration with an arbitrary beam setting of 5 kV and a few hundred picoamps. Naturally, this is going to charge the sample, so I drop the acceleration voltage down in steps to 2 kV, then 1 kV, then 500 volts, and then 200 volts. You'll notice that the field of view stays relatively the same as this is done, and the user just needs to perform minimal focus and stigmation correction to get a sharp image at each setting. We follow this up with dropping the current down to 6 picoamps at 200 volts to remove any residual charging. This video is playing back at a speed of 3 times its original speed, but the timer in the top left is scaled with that and has been counting ever since the imaging session started on this sample. And as the final tweaks are being performed on focus, stigmation, and wobble, we can see that we can collect a very nice image on this non-conductive and beam-sensitive sample in less than 4 minutes. We'll follow this up with some even higher magnification images all the way up to 100,000x. The beam settings here are the same at 200 volts and 6 picoamps. The beam tuning is done at this higher magnification. And you'll notice that as we build the image, we're going to utilize this drift-corrected frame integration with a very fast scan speed. By utilizing a fast scan speed, we can avoid charging within the sample. And with the drift-corrected frame integration, we can build an image using frame averaging with that fast scan speed. The drift-corrected nature of it allows us to also have a registration image to image in that frame averaging, so that if there's any minor drift from charging, that is eliminated from the image. We're also utilizing Y-interlace, which allows the system to collect a single frame with non-sequential lines. So instead of the image building line 1, then line 2, then line 3, I can specify a scan interlace factor, and we can raster line 1, then line 6, then line 2, then line 7, line 3, and line 8 to spatially break up our dose onto the sample. So thanks for bearing with me there. I think I had a small mistake with playing the wrong video, but I just wanted to prove that we're live. So I wanted to share one thing I really liked about that video was the ability to move around, especially once we were at 100,000x magnification, and just sort of snap pictures wherever I wanted. So there is a question area. If there are any questions, please feel free to submit them. We'll be happy to take those questions. With that, I'd like to point you in the direction of some resources. So we have some upcoming ZMCC workshops. I'm actually going to be hosting one next Friday on a very, very similar topic, expanding on what was talked about today, high-resolution imaging on the 𝗶ₚ 560 with non-conductive samples. There's also workshops across our XRM and LM suite. We have the ZEISS portal, which, among many other things, has a repository of training videos for different users if you wanted to brush up on some skills across, again, the XRM, LM, and EM suites. And then all the way on the right, we have some upcoming live streams that I had shown earlier in the stream. Of course, we have a subscribe button if you'd like to subscribe to our YouTube channel for updates and notifications on our future streams and videos. So with that, I'd like to thank you very much for joining us today in the 10th Micro Minute session, and I hope you have a great day. Bye-bye.